Have you ever found yourself looking at a complex subject, maybe something like mathematics, and felt like you were just seeing a jumble of disconnected facts? Like you
Mm.
knew what to do, maybe, but not really why it worked or how it all connected.
Yeah, that's a really common feeling, I think, especially in math.
Right. But what if there was a way to cut through that information overload, to find the essential threads, the surprising insights, and really get the why behind the what?
That would be ideal.
Well, today we're taking a deep dive into exactly that kind of intellectual journey, and we're guided by a real visionary.
Sounds fascinating.
Our core material for this is a foundational work by the renowned mathematician Felix Klein, Elementary Mathematics from a Higher Standpoint.
Ah, Klein, a
And
giant.
indeed. Now, that title, Elementary Mathematics, it can be a bit deceptive, can it?
It really can. People hear elementary and think simple.
Exactly. But this isn't about simple math, not really. It's about uncovering the fundamental concepts, the deep connections that even experts, especially teachers, sometimes overlook.
Mm.
Our mission today is to really understand Klein's revolutionary approach to teaching math.
An approach aimed at making the complex deeply understandable, right,
Yeah.
by building up from a solid foundation.
Precisely.
And it really was a profoundly influential reform effort, particularly back in the early 20th century. Klein's lectures, which these volumes are based on, they were specifically designed for future high school math teachers at Göttingen University.
So, aiming to improve teaching right from the source.
Absolutely. His goal was to dramatically improve secondary math education by, well, fundamentally changing how teachers themselves understood the subject. He wanted a holistic vision, no sharp disconnect between school math and university math.
And that word elementary, you said it's misunderstood.
Often, yes. For Klein, it meant exactly what you said earlier,
Yeah.
getting to the fundamental conceptions, the very elements of a topic. It wasn't about trivializing things.
Ah,
It actually has these deep historical roots, going back to Enlightenment figures like D'Alembert. He wanted to elementarize sciences, connect the parts to the whole, show the coherence. Klein really picked up that torch. True understanding comes from seeing the big picture, not just isolated bits.
okay, let's unpack this then, starting right at the beginning. Numbers. We kind of take them for granted, don't we?
We really do.
So think about the simplest ones, natural numbers. How did Klein bridge the gap between how they're handled in schools, maybe intuitively, and the rigor needed from this higher standpoint?
Well, he starts by laying out the 11 fundamental laws of arithmetic, for addition and multiplication.
Things like commutative, associative laws.
Exactly. Closure, unique value, associative, commutative, the monotonic law, which basically says inequalities behave nicely when you add things, and the distributive law connecting addition and multiplication.
Okay.
And he makes this key point. While these properties seem totally obvious from our intuition, our notion of quantity,
Like 2 plus 3 is the same as 3 plus 2, yeah.
right, obvious. But he insists they must be formally peeled out, as he puts it. They need to be explicitly stated to logically support everything that comes later in mathematics.
So it's not just being pedantic, it's about building that logical foundation.
Precisely. It unlocks the possibility of creating these rigorous, self-contained mathematical systems. And historically, you see this push towards formalization.
Like with Grassmann.
Yes, Hermann Grassmann derived the commutative law from the associative law using induction. A big step, showing even obvious rules could be derived logically.
And then Piano took it further.
He did. Giuseppe Piano developed this unique symbolic language, really designed to strip away all intuitive meaning. He wanted to guarantee every step was purely logical, avoiding uncontrollable associations of ideas.
Making math less about intuition, more about logical machinery.
In a sense, yeah. And that leads us straight to David Hilbert.
Hilbert's formal theory, where symbols are just things.
Pretty much. Things devoid of meaning, or at least meaning we don't need to worry about for the logic itself. The operations are just rules for manipulating these symbols.
Which brings up his famous consistency problem.
Exactly. The huge challenge. Can we prove, purely logically, that these fundamental laws will never lead to a contradiction? Hilbert thought the certainty of math rested on this.
But Klein saw something missing there, didn't he? Even if you prove logical consistency.
Right. Klein's crucial insight was that proving consistency logically doesn't, by itself, establish what he called The proper arithmetic, the theory of actual integers.
Meaning?
Meaning, pure logic can show the system won't contradict itself, but it can't prove that this system perfectly matches our real-world understanding of numbers and counting.
Ah, okay.
Hello?
So there's a gap between the logical game and reality.
Yes, for Klein, justifying arithmetic has two parts. There's the purely logical problem establishing consistency, that's pure math. But then there's the epistemological part, justifying the application of these logical laws to actual conditions. And for Klein, that step belongs to applied mathematics. Pure and applied math are intertwined for a full understanding.
That connects to his analogy about math growing like a tree, right? Not just upwards from tiny roots.
Exactly. It's such a vivid image. Mathematics has grown like a tree, sends its roots deeper and deeper at the same time and rate that its branches and leaves are spreading upward.
So discovery isn't just top-down deduction.
Not at all. Klein argued that productive math uses fantasy, proceeds inductively, explores. It's not just rigid logic, and that's why applications are absolutely vital.
The living thing in mathematics.
Yes, logic is the rigid skeleton, essential for structure.
Yeah.
But the living thing, its most important stimuli, its effectiveness outwardly, depend entirely upon the applications.
Wow. He put it strongly.
He really did. To banish applications would be comparable to seeking the essence of the living animal in the skeleton alone. You need the whole organism, the connection to the world.
Okay, so building on that, let's look at how number systems themselves evolved. After natural numbers, Klein points to negative numbers as this: extraordinarily difficult conceptual hurdle for students. Why?
Well, think about it. It forces this shift away from concrete visual quantities, things you can hold or see, towards abstract, formal mathematics. Suddenly, numbers aren't just counts. They represent, well, something else. Direction, debt.
And historically, they weren't just invented cleanly.
Not at all. Klein points out they forced itself, so to speak, upon mathematicians over centuries. People used them because they were useful long before their logical consistency was properly tackled in the 19th century.
So utility came first, justification later.
Pretty much. And this led to that uneasy conscience some older mathematicians had.
Which brings us to Hankel's principle.
Right. Hermann Hankel's principle of permanence of formal laws. It basically describes our tendency to apply rules under more general conditions than where they first came from.
Like extending rules for positive numbers to negative ones.
Exactly. Like figuring out that DD must equal BD if you want the distributive law to keep working consistently. But it felt weird. They called them invented or false numbers.
And this historical unease seeped into teaching.
Unfortunately, yes. Klein really criticizes schools for often making the error of trying to prove the logical necessity of the rule of signs.
Trying to prove something that can't really be proven in that context.
Right. They confuse a plausible reason, a heuristic derivation, with a real logical proof from axioms, which isn't how it works at that stage. And that just mystifies students. It mixes up how we discovered or justified it with why it's logically defined that way now.
Okay, so after the negative number hurdle, what about fractions? Another seemingly simple concept.
But again, a conceptual shift. The typical school approach uses measurable quantities. Cutting pizzas, sharing coins, gives a concrete feel.
Makes sense.
But the modern mathematical conception, it stays entirely within the realm of integers. Fractions are defined formally as number pairs. It's a move from tangible division to abstract structure.
And then irrationals, the square root of 2.
Which definitely came from geometry, right? Pythagoras, the hypotenuse of that simple right triangle. You can draw it, but you can't write it as a ratio of whole numbers. Incommensurable.
And decimals helped formalize this idea.
Kind of automatically, yeah. Once decimal fractions were introduced in the late 16th century, people knew rational numbers either terminated or repeated as decimals.
So the idea of a decimal that doesn't repeat.
Just going on forever, periodically, seemed like a natural way to define these other non-rational numbers.
But the rigorous foundation came later.
Much later, 19th century. Georg Cantor, the founder of set theory, and Richard Dedekind. Dedekind's definition using a cut in the rational numbers is classic.
Explain the cut idea briefly.
Basically, you divide all rational numbers into two sets, A and B, where every number in A is less than every number in B. That division point, that cut, is the number. If the cut happens at a rational number, fine. If it happens between rational numbers, that defines an irrational number.
And he called this an arbitrary convention.
Well, from a purely logical standpoint, it is. It's a definition we choose because it works consistently. It's not discovering something already there in the same way as finding a rock. It shows math involves construction.
And this definition rigorously proves things like 0.999 equals 1.
Exactly, because the cut defined by 0.999 is identical to the cut defined by 1. There are no rational numbers between them. The difference is 0.
Mind-bending stuff. But it had practical ties, too. You mentioned Memke.
Rudolf Memke, yeah. He categorized calculations into exact and approximate, a super important distinction in science and engineering.
And Klein was interested in calculating machines.
Oh, yes, he found the mechanics most ingenious. He talks about the Bruns-Viga calculator and how the mechanism for carrying the tens, when a wheel clicks over from 9 to 0 and nudges the next wheel, is a physical embodiment of arithmetic principles.
Like seeing the math in the gears.
Precisely. Tangible math.
Okay, moving on to the next big extension. Complex numbers. I, the square root of -1. Klein notes their initial, somewhat mystic coloring.
Definitely. Leibniz's famous quote about them being a fine and wonderful refuge of the divine spirit, almost an amphibian between being and non-being. There's real discomfort.
But they proved useful.
Incredibly useful. Cardan used them back in 1545 for solving cubic equations.
Yeah.
And then Euler, mid-18th century, discovered that fundamental relation ex plus I sens.
That's huge, connecting exponentials and trig functions.
Absolutely. Suddenly, these imaginary numbers were weaving together algebra, geometry, calculus in profound ways. Utility drove acceptance again.
And Gauss provided the geometric picture.
Carl Friedrich Gauss, yes.
Yeah.
He'd conceived it in 1797, though didn't publish until 1831. Visualizing complex numbers as points on a plane, he called it the true metaphysics of imaginary numbers.
Justifying them by intuition, not just formal rules.
Exactly. And he suggested the term complex instead of imaginary, which, thankfully, stuck. Is much better.
So formally, they're defined as pairs of real numbers.
Right. Number pairs, x, y, with specific rules for adding and multiplying these pairs. And interestingly, the monotonic law, the idea of simple ordering by size, breaks down here. You can't easily say one complex number is bigger than another in the same way.
Gauss also worked on integer complex numbers.
Yeah, generalizing number theory concepts like primes and divisibility into this new complex realm, really expanding the field.
Okay, here's where it gets really interesting, as you said. Pushing beyond complex numbers, higher complex numbers.
The most famous example being quaternions, pioneered by William Rowan Hamilton.
These have 4 terms, not just 2.
4 terms, yes.
Yeah.
And the absolute kicker, their multiplication is non-commutative.
Meaning PQ is not necessarily the same as QP.
Exactly. That's a massive departure from standard arithmetic, a radical conceptual leap.
But they still found uses, even being non-commutative.
Oh, yeah. Their unique structure turned out to be perfect for describing things like rotation, dilation, and 4-dimensional space.
4 dimensions.
Yeah, connecting to early ideas in physics, like electrodynamics and relativity, through Minkowski's work. Hamilton's quaternion formula actually packs all of Euler's complex rotation formulas into one neat package.
So incredibly powerful for specific things, but why didn't his general quaternion calculus become mainstream?
Largely because of that non-commutative nature. It made it too different, too isolated from the rest of mathematics. It didn't develop those vital relationships and interdependencies Klein talked about. It was powerful, but niche.
Fascinating. It's like a branch that grew strong but didn't connect back to the main trunk easily.
That's a good way to put it. Oh, and Klein shares this amusing anecdote from Kessner about the word algebra.
The bone setter.
Yeah, from the Arabic, for a surgeon mending broken bones. Kessner jokingly suggested it was about making fractions whole, finding common denominators, a reminder of concrete origins.
Love it. So, bringing this back to teaching complex numbers today.
Modern teaching, like in Barty's textbooks Klein mentions, really adopted his ideas. Present complex numbers as a natural extension. Use the geometric interpretation heavily. Avoid the old mysticism.
Make it intuitive.
Right, which leads to Klein's core belief about teachers. Their knowledge should be far greater than that which he presents to his pupils.
Knowing the cliffs and whirlpools.
Exactly. Must be familiar with the cliffs and the whirlpools in order to guide his pupils safely past them, even if the students don't go deep into function theory. You need that depth to teach effectively, to anticipate the tricky spots.
That idea of deep, holistic understanding perfectly sets up Klein's distinction between Plan A and Plan B for mathematical development.
Yeah.
What are these 2 paths?
Okay, so Plan A is what Klein saw as the typical approach in schools and textbooks back then. Very formal, very sequential. It starts with formal equation theory, then separately logarithms and trig functions, then algebraic analysis, infinite series, Euler's formula x equals x plus I sin x. And finally, the rigorous 19th century convergence stuff from Gauss, Abel, Cauchy. Logical, yes, but fragmented.
Feels like separate boxes of knowledge.
Kind of. Now contrast that with Plan B. This one focuses on analytic geometry.
The fusion of number and space.
Exactly. Here, ideas like the differential quotient slope and the integral area, they arise naturally from looking at curves. New functions, like logarithms, can emerge organically from geometric problems, like finding the area under a hyperbola.
Much more interconnected from the start.
Totally. And Klein strongly preferred Plan B for teaching. He asked rhetorically, one cannot well be in doubt as to which of these two methods has more life in it, as to which would grip the pupil more.
Because it shows the why more clearly.
Yes. In Plan A, x and sin x seem to come from different worlds. Plan B shows why they're deeply connected through Euler's formula, visualized geometrically, and why they pop up of their own accord in so many different areas. From finance to physics, it feels more alive.
So what does this mean for you, the learner? How did Klein apply Plan B practically?
Well, take solving equations. Instead of just symbolic manipulation, he showed how you can visualize finding real roots. Imagine a curve, say a cubic parabola y will by 3 plus px plus q.
Okay.
Finding roots means finding where y is 0, but you can think of it as intersecting that curve with a moving horizontal line, y goes q. As you slide the line up and down, changing q, you can literally see how the number of intersection points the real roots changes.
Making the abstract visual.
Exactly. And he even highlighted physical models for this. Rudolf Memke had this apparatus, a frame, with rods and templates for standard cubic quadratic curves to find roots mechanically.
Wow, and Hartenstein's model.
That used stretched threads to represent surfaces, visualizing solutions in higher dimensions, really trying to make abstract math tangible.
This connects to those ancient impossibility problems too, right? Trisecting the angle, constructing a regular heptagon.
Yes, Klein explains how these problems, when translated into algebra, require solving certain irreducible cubic equations that simply cannot be solved using only steps equivalent to ruler and compass constructions, which correspond to square roots.
So it's mathematically impossible with those tools.
Correct. And for angle trisection, it's even a bit more subtle. It involves function-theoretic irreducibility, not just number-theoretic. But the conclusion is the same. The endeavors of angle trisection zealots must always be fruitless. Understanding the limits is key.
Okay, from the impossible to the transcendental. Let's talk about numbers like pi and e.
Transcendental numbers. These are numbers that go beyond even algebraic numbers. They cannot be the root of any polynomial equation with integer coefficients.
Unlike, say, the square root of 2, which is the root of by 2 equals 0.
Exactly. Pi and e are the most famous examples. And the proof that pi is transcendental finally settled that ancient quadrature of the circle problem.
Making it impossible to square the circle with ruler and compass.
Correct, because constructing a length with ruler and compass corresponds to algebraic operations, primarily square roots. If pi isn't algebraic, you can't construct it that way. The proofs themselves are clever, often using integrals in a way that assumes the number is algebraic and then forces a contradiction, like showing an integer must be between 0 and 1.
It's hard to visualize how many of these numbers there are.
Right. Rational numbers are dense, algebraic numbers are also dense. But the transcendence theorem shows there are still infinitely many other numbers, the transcendentals filling the gaps. Klein uses the example of the curve y equal x. It passes through infinitely many points where if x is algebraic and not 0, y must be transcendental. They're everywhere, in a sense.
And this very existence spurred Cantor's work on set theory.
Precisely. Georg Cantor started his investigations into the infinite because of the existence of transcendental numbers. He wanted to compare the sizes of different infinities.
Which brings us to potency of sets, comparing infinite sets.
Yeah, asking, are all infinities the same size? Think about the set of positive integers, 1, 2, 3, the set of all rational numbers, fractions, the set of algebraic numbers, and the set of all real numbers, including transcendentals.
Are they different sizes of infinity?
Cantor's great discovery in 1873 was stunning. He showed that the positive integers, the rational numbers, and even the algebraic numbers all have the same potency. They are denumerable or countable.
Meaning you can put them in a one-to-one list with the integers.
Theoretically, yes, like using a clever counting by diagonals method for fractions. But, and this was the bombshell, the set of all real numbers, the continuum, has a larger potency. It's not denumerable.
You can't list them all.
Nope. His famous diagonal procedure proves that no matter what list you make, you can always construct a real number that isn't on it. It's a fundamentally bigger infinity.
Wow. And then there's an even more mind-bending result.
Ah, yes. The set of points on a tiny line segment has the same potency as the set of all points in a square, or even a cube.
How is that even possible? More dimensions should mean more points, shouldn't it?
Intuitively, yes. But Cantor showed you can create a one-to-one mapping. Essentially, you interleave the infinite decimal digits of the coordinates. A point xy in the square can be mapped to a single point z on the line by weaving their decimal expansions together. It breaks our geometric intuition, but works logically.
Unbelievable. But Klein adds a caution here, right? About just focusing on size.
Yes, a crucial point often missed. He stresses the importance of the arrangement of the elements of a set. Knowing two infinite sets have the same size, potency, doesn't mean they're structured the same way.
Like integers versus rationals.
Exactly, both are denumerable. But integers are neatly ordered 1, 2, 3, while rationals are everywhere dense. Between any two, there's another. Set theory shouldn't just count. It should help us grasp these deep structural differences.
And how does this all circle back to teaching, to pedagogy?
Through Klein's idea of the biogenetic fundamental law, he argued that math instruction should generally mirror the historical development of human understanding.
Start simple and intuitive, then build up.
Yes, guide students slowly to higher things, and finally to abstract formulations, starting from their naive original state. He directly challenged the approach of starting with the most abstract general definitions. First, what he called the way of medieval scholastics.
Build from intuition, not just logic down.
Right. And to wrap up that pedagogical thread, Ernst Study, a contemporary, gave some nuanced advice on teaching calculus in schools.
What was his take?
He agreed with Klein that a full, rigorous, systematic course wasn't appropriate for secondary schools. But he strongly advocated introducing specific calculus concepts, notations, and key results.
No.
In a simple manner and using concrete examples as far as possible, especially graphical representations. Avoid jargon and overly general statements students can't grasp. The goal is to direct their interest effectively, to show them the power and beauty without overwhelming them. Cultivate understanding, not just memorization.
So we've journeyed from the very definition of numbers through negatives, irrationals, complex numbers, even quaternions, touched on impossible problems, transcendence, and the bewildering nature of infinity. All through Klein's lens. What really stands out, I think, is how even elementary math is just brimming with history, with human struggle, with these deep philosophical questions. It's not static at all.
Not in the slightest. And understanding those nuances, the history, the difference between formal logic and intuition, the ways math grows like that tree, it just enriches your appreciation, doesn't it? It shows mathematics as this living, evolving thing.
Absolutely. So what does this all mean for you listening? Maybe the next time you bump into a mathematical concept, even one that seems simple, pause for a second. Think about the centuries of thought, the debates, the unexpected twists that might be hidden inside it. How might understanding that deep dive history change your relationship with knowledge? Not just in math, but maybe in everything you explore.